This is number 69, part A from chapter 18. It asks us to calculate the equilibrium constant for the following process: 2 carbon monoxide plus O2 as a gas is in equilibria with 2 CO2s. And we want to know what is our equilibrium constant equal to at 25 degrees Celsius. So what we want to use is our relationship with delta G at standard state to our equilibrium constant. And so our delta G at standard state is equal to negative RT natural log of K. And what we want to do is solve for that delta G by looking up our heats of formation of our products and our starting materials. And so we want to take the difference of those two. And so that would mean that our delta G would equal 2 times the delta G of formation for CO2 minus 2 times the delta G for carbon monoxide plus the delta G of formation for oxygen as a gas. Start to plug in these values. Our delta G would be equal to 2 times negative 394.4 for our CO2 delta G. Our carbon monoxide would be 2 times 137.2, negative 137.2. And then our delta G for oxygen, remember, is going to be 0. Delta G and delta H for elements as they appear naturally is always 0. And so from this, we can solve for our delta G to be equal to negative 514.4 kilojoules per mole. We can now use that delta G back to the first equation to now answer the problem by solving for what K is. And so if we substitute our values that we know, our delta G is at negative 514.4. Let's make some more room here. Let's go down here. It's negative 514.4 kilojoules per mole. That's equal to negative R. I'm going to do the conversion to kilojoules for that constant, times our temperature, which is 298, or 25 degrees Celsius, and what we're solving for, that natural log of K. So I just substituted what we solved for in the first part into that delta G expression. And so now we're manipulating this expression. So we bring over our R and our T. We would have negative 514.4 over a negative 2.477. And so that would equal the natural log of our K. Our K would then be equal to E, right? The E function is getting rid of the natural log. And if we take the fraction of 514 over 2.47, we get 207.62. And we take E to that value, and we end up with our equilibrium constant for this process to be 1.476 times 10 to the 90th. I know it's quite large equilibrium constant, but that is the answer for 69, part A, chapter 18.